G'day team, welcome back to another video, and today we are going to be continuing our work with the unit circle and trigonometry. So today we're actually going to develop the unit circle a little bit. I'm going to sort of explain how it sort of works, where things come from, why things are what they are. So a unit, typically in maths, we state is one of something. So the unit circle is the circle with the center 0, 0, so at the origin, and has a radius of 1. Now, if you're thinking back to when we were doing our function work and we're actually working with circles and the equations of circles, you would know that the equation of our unit circle would look like x squared plus y squared equals 1, which you can see here. So it's x, take the x coordinate of our origin, y, take the y coordinate of our origin all squared, and then our radius squared, so 1. All right, so please keep this in mind because we are actually going to jump back to this a little bit later on in this video. Now, with the unit circle, we will be given positive and negative angles, okay? So in this diagram, we've let P be the point at 1, 0 on the unit circle, so over here. And Q can lie anywhere on our unit circle, so I've put Q over here. Now, if I'm measuring theta and it's positive, it's just like a normal angle. It goes anti-clockwise, all right? If theta is negative to Q, then we measure it clockwise, all right? So theta is positive for anti-clockwise rotations, and theta is negative for clockwise rotations, okay? So this is a really important fact that we are going to use quite often in this unit of work. So please make sure you are all over which way positive angles are measured and which way negative angles are measured. All right, so a quick example of this. So theta equals 135 degrees or 3 pi over 4 radians. We can see that's positive, so we measure from the positive x-axis all the way around to 135 or 3 pi on 4 radians. Now, theta equals negative 225 or negative 5 pi on 4 radians. We're actually going all the way around this way clockwise. And funny enough, we actually end up in the same spot. So 135 degrees is actually equal to negative 225 degrees. And I'm actually missing some units, all right? So that's how positive and negative angles are measured. Now, let's actually use and define cosine and sine for our unit circle. All right. So I have my unit circle here at the origin, angle theta, and we're extending our radius to a point P with coordinates A and B. So x coordinate is A, B coordinate is, the y coordinate is B, sorry. So A is defined to be how far across the right or horizontally we've gone, so that's A, and B is how far we've moved vertically. And then the hypotenuse, or this line here, is the radius of our circle, which we've defined to be 1. Now, if you're thinking back to our trigonometric ratios that we looked at the start of this playlist, we'll remember that SOHCAHTOA, so sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, and tan equals opposite over adjacent. Now, we've defined opposite, adjacent, and hypotenuse with B, A, and 1 respectively, okay? Cos theta, now that's adjacent over hypotenuse, which is A divided by 1. Anything divided by 1 is A. Sine theta, same thing, but opposite over hypotenuse. The opposite we've defined to be B. B divided by 1, again, anything divided by 1 is itself, so sine theta equals B. And then we get a bit of a funny result here. So tan theta is actually B divided by A, but up here we've defined sine theta to be B and cos theta to be A. So we've actually got tan theta equals sine theta over cos theta. Now, hold on to that because we will come back to that a bit later. But the two major results I want you to realize in this little section here is that cos theta is the x coordinate of P and sine theta is the y coordinate of P. So remember up here, cos theta equals A, but over here, A is actually the x-coordinate of P. Sine theta equals B, and over here, the y-coordinate is B. So cos theta equals X, sine theta equals Y. Okay, so that's the two big sort of things we're looking at here, all right, and that will help in the questions that will come to follow. So an example, if I have an angle measuring 2 pi on 3 radians, the line that is extended by this angle, so the point on the unit circle here, the x-coordinate will be cosine of this angle, so 2 pi on 3. And then the y-coordinate will be sine of this angle, so sine of 2 pi on 3. Now I've put in a coordinate here. Now I want you to pause, just think about it. What angle do we think will wrap all the way around to create this line here that touches the unit circle at the point cosine 4 pi on 3 and sine 4 pi on 3? So take a quick moment, just have a think about it. So hopefully you're starting to get the idea now, and you actually said that this angle has to be 4 pi on 3, okay? So all we're doing is looking at the angles in here, and that is the angle of our extending radius here, all right? So remembering back when I said at the start of this video, the equation of a unit circle is x squared plus y squared equals 1. So we actually just defined that x is cos theta and y is sine theta. So this equation now becomes cosine squared theta plus sine squared theta equals 1. Now we treat this as cos theta all squared. In maths and trigonometry, we just write it like this. So you'll see it like this. But if you're told a cosine theta value and we're substituting into this equation, then it's that value squared, okay? But this result here, all right, cos squared theta plus sine squared theta equals 1 is actually a really, really crucial trigonometric identity, okay? It is the first one we look at, and there are a lot more to follow, but this one is probably the most used one that you will come across at this level of maths, all right? So it's really important that we get this formula down, because we will be using this a lot in the next video and future videos, all right? So for all points on the unit circle, our domain, so what values our x coordinate can take, range from -1 to 1, and our range, so the values that our y can take, also range from -1 to 1. But again, x is cos theta and y is sine theta. So that means cos theta has to be between -1 and 1, and sine theta also has to be between -1 and 1, all right? So they're our domain and range for cos theta and sine theta. Now, last little thing before we get into a couple of examples, all right? So as we saw above, tan theta equals sine theta on cos theta, but sine theta is the rise of our hypotenuse, okay? And cos theta is the run of our hypotenuse. So if we define the origin to be point O, and we've got point P, then tan theta is equal to the rise over run. And if you remember from like year 9 maths, that's the gradient of the line OP. So tan theta is the gradient of our hypotenuse, all right? So please keep this in mind when we are working with tan. Now I've gone ahead and drawn out the whole unit circle, okay? So this is the full unit circle here. I don't actually have my tan values on my coordinates here, but we can quickly put those in. So sine over theta, 0 over 1 is 0. 0 over -1 is 0. But now we've got 1 over 0 up the top here, and -1 over 0 on the bottom here. Anything divided by 0 is undefined or does not exist. So our tan values at pi on 2 radians and 3 pi on 2 radians actually doesn't exist, all right, or is undefined. So hopefully you have a unit circle at home. You can print one off from the internet, all right? One thing I want you to notice is this value in here. So this 1 on root 2, you may see as written as root 2 on 2, all right? Now, both are completely correct, and you can use either of them however you like. I tend to use the 1 and root 2 just because it looks a bit simpler, but the choice is completely up to you. All right. Last little thing before an example. I know this is a fairly chunky video, but please bear with me. So the signs of the coordinates, sine, cos, and tan, can be determined by remembering what quadrant they'll be positive in, okay? So when I was in year 9 or year 10, I was taught to remember South Australian Tennis Club. I'm from South Australia, so SATC. You can also remember it as All Silly Turtles Cruel. However you prefer to remember it, make your own acronym, that's more than fine. Now, in this quadrant, in the all quadrant or quadrant 1, every single value, sine, cos, and tan, will be positive, okay? In quadrant 2, only the sine values will be positive. In quadrant 3, only the tan values will be positive. And then finally in quadrant 4, only the cos values will be positive, okay? Super important that we are remembering this because it will become like second nature and you'll be able to figure out what values you should be. And you'll be able to determine through reasonableness if you're actually getting the correct answer. All right, so first example, use a unit circle to find the values of cosine 135 degrees and sine negative 120 degrees. 210 degrees, not 120, 210. All right, first of all, cosine of 135 degrees, all right. Jump up to your unit circle and locate 135 degrees. Now, I know that's over 90 degrees and below 180, so I know it's going to be in my quadrant 2. So I can actually see him here, and we want to find the cosine of 135. So that's my x coordinate. So we're looking at negative 1 on root 2. All right, and it is simple as that. Now, sine of negative 210, all right. Back up, so negative 210, that's a bit trickier to work out, but I like to look at it in relation to 180. So starting here, negative 210, so negative all the way to 180. 210 is 30 more than 180, so that goes to positive 150 degrees or positive 5 pi on 6 radians. And we're looking at the sine value, so the y coordinate there, which is positive 1/2. All right. So it is as simple as that. Now, if you are following along the Hazy textbook, I want you to have a crack at chapter 5C, questions 1 through 4. All right, we've split this chapter in half, so might not be able to answer the questions after that just yet, but tune in for the next video and we'll be more than fine. We'll see you guys next time. Thanks for watching.